much water flows in the river during low flow periods, because these are the most critical conditions. When I have a flood, water resources, the water withdrawal is my last problem. I have a lot of water, so I'm not concerned about water withdrawal. I am concerned when there is no water. So you have to refer to low flows. And not just to the minimum, but to low flows over a long period, like summer. So I need to know the hydrograph, not just a point of the hydrograph. Therefore, this is an important limitation of the rational formula. And which must be solved, of course. And therefore, we have to increase the complexity of the model. But let's make an example. An example accordingly to which we can extend the rational formula to simulate the hydrograph. The first idea that we may have is, okay, but I have the rational formula available. Can I use the rational formula to estimate the hydrograph, not just the result? This is possible. And in fact, the rational formula is a special case of a more complex range runoff model. I mean, you can make the rational formula a bit more complex in order to simulate the hydrograph. And I want to give you also this example because, again, it clarifies the type of approach that we have to follow. And the example is an example of a model which is called time area model or time area method. So let's talk about the time area method. This model or model, these two terms are used interchangeably, like synonyms. This model in Italian is called modello di corrivazione or modello cinematico, two terms. I prefer to use in Italian modello di corrivazione because by saying modello cinematico there are many models that are called kinematic models, so I prefer to call it modello di corrivazione. And I'm sure that you know it because it's the first model that is illustrated in the hydrology courses, so I'm sure that you know it. I want just to record the basic concepts because it's useful for me and for you to start from a very simple case. And the time area method refers to a catchment and uses an approach that is very similar to that is used by the rational formula. The time area method imagines that when it rains, you have these drops that are start traveling downstream to reach the outlet. And again, it makes use of the concept of the concentration time. So it relies on the computation of the time taken by each drop to reach the outlet. Again, this time is assumed to be depending only on the geographical location. So the time taken by the drops is not changing in time. It's the same in winter, summer. It's just depending on the geographical location. And therefore, under the simplifying assumption, which is, of course is not true, but it's very helpful. It's not true because drops travel at a different velocity in summer and winter. So the time taken by the drops to travel downstream is different in the different seasons. But let's assume that is a constant. Depending only on geographical location in the catchment, then when it starts raining, you can reconstruct the river flow at the closure of the catchment by just summing the contribution of each drop. This is the idea. And in order to do so, we need to identify the time taken by drops to reach the closure for each point of the catchment. For each point of the catchment. And therefore, if we do so, we can connect the points that have the same travel time. These lines, like for instance, this one would be the line that connects all the points that have a travel time of 1 hour. These are isolines, in Italian are called isocorrive. I'm not sure about the term in English. I think could be isochrone lines or something like that, but I don't remember it well really. But in any case, it's important the concept, which is this line connects all the points such that drops that fell over these points take 1 hour to reach the outlet. So it's quite intuitive that downstream you have a travel time that is lower than 1 hour, and upstream you have longer travel times. And then you can also draw another isoline for 2 hours, another one for 3 hours, and maybe say that 4 hours is the isoline which reduces to, in this case, for simplicity, to just 1 point, which corresponds to the concentration time of the catchment. So let's suppose that you have a way to identify these lines. And of course, this is not easy. There are some empirical formulas to compute the travel time, but these empirical formulas are affected by much uncertainty. I'm not giving you examples of empirical formulas because they are very difficult to remember. I just give one example for the computation of the concentration time, because the concentration time, I forgot to say this before, but it's not too late. The concentration time, the computation of the concentration time is resolved by using empirical formulas, and the estimate is affected by much uncertainty. And there are several different empirical formulas. I just mentioned one now. And if you make a comparison for the same catchment, you compute the concentration time with 5 different empirical formulas, you get indication that differ maybe for 200%. One formula gives to you 10 hours, another one gives to you 2 days, unfortunately. It's not easy to compute the concentration time. I just give you one example because it's a formula that is used in Italy, which is the Giandotti's formula. I'm not assuming that you remember it. I remember Giandotti's formula because it's a very frequently used formula, so I remember it, but I'm not assuming that you remember it. It's very difficult that I ask you Giandotti's formula. Maybe just because I am in doubt if whether or not I should give to you the laude, and so maybe that I ask Giandotti's formula, but it's very difficult. I hope I clarify the concept. And Giandotti's formula is I said that I remember it, but it's 4 times the square root of A is the area of the catchment, times 1.5 plus 1.5 times L. L is the length of the main stream. A catchment typically you have a main stream that starts from the outlet and stops somewhere. And this is the main stream, and at the denominator you have 0.8 times the square root of h. H is the average elevation of the catchment with respect to the closure section. And be careful, here area is expressed in square kilometers. L is expressed in kilometers, elevation in meters. So it's not dimensionally homogeneous, this formula. You can understand uncertainty here, because, you know, it's clear that it's empirical, okay? This is a formula that can be used for computing the concentration time. In principle, you could use it also for computing the travel time in each point of the catchment. Usually this is not done, because it's too imprecise. What is usually done is to use Giandotti's formula to compute the concentration time, and then it's assumed that the travel time in each point of the catchment is proportional to the basin area at that point. I better explain. Let's assume that you have at this point, which is the point located much far from the closure, you have a concentration time of 4 hours and an area A of the catchment. Okay, let's assume that then that you want to compute the travel time for this point here, where you have, or this point, sorry, for this line here, because it's the same travel time. And let's assume that the area, the downstream area, is A2 plus A1. So let's assume that the first line has a downstream area of the catchment, which is A1. Let's assume that the second line has a downstream area that is given by A2, which is the inter area, plus A1. Then you can compute the travel time in this way. You may say that T is equal to Tc divided by A times A1 plus A2. So the concentration time is divided by the total area of the catchment, and then we multiply this ratio for the downstream area, the total downstream area of the considered isoline, and we get time 2. Let's say time 2. This is what is usually done, which is, again, affected by much uncertainty. Is it clear? Okay. Accordingly to this simplification, we can compute the position of isolines. Okay? And now, once that we have the isolines displaced, you need one more assumption, indeed, to compute the position of isolines, and because it's not just enough this assumption here. You need one more assumption, which is an assumption that the travel time is proportional to the distance, to the shortest distance to the basin outlet. Okay? I try to better explain, but you need a second assumption, please.
No, A2 is equal to A1 plus.
You don't understand here?
A2, for example, A2, A3, what is the minus?
A1 is this area here. A2 is this one. It's inter area. Okay?
So it's not plus A1.
No, A2 is the downstream area for this isoline here is given by A2 and A1. This is important that we agree on this. Okay? Let's say that AI is the inter-area. Okay? And what is the reason why I said you need one more assumption, namely the assumption that point line on the isolines have an equal distance, an equal shortest distance with respect to the outlet, because otherwise you may, if you just use this relationship, you may use it, for instance, for computing the travel time T2 of refer to the isoline that downstream as an area of A1 plus A2. So let's suppose that you have a total catchment area of 10 square kilometers with a concentration time of 10 hours. Then, according to this relationship, you can say that if an isoline has a downstream area of 2 square kilometers, then the concentration time is 2 hours. But still, you don't have the displacement. You need to, you don't know where is the position, because you know the downstream area. But of course you don't know the position, because you could draw different lines that have this downstream area. If you don't assume, in order to make the line unique, you have to assume that the travel time is proportional just to the distance. And then you can draw at this point, once that you know that points on this isoline have a given downstream area and the same downstream distance, then you get a unique isoline. Okay? Because otherwise, you know, you could draw this line here or another one here, and you have the same downstream area, but of course the distance is different. You need to make explicit that the distance of the point is the same, and then you get a unique displacement of the isoline. Okay, so let's assume now that we are able to identify the position of these isolines, and let's now think about what happens when it starts raining. And let's assume that the rain lasts for a long time. Okay? So, I draw again the catchment because I want to make it bigger. So we have here the isoline of 1 hour, 2 hours, and let's say 3 hours. And let's indicate with A1 the first area, A2 is an inter area, so A2 is just this one, and A3 the third area. So we can write that A total area is equal to A1 plus A2 plus A3. Good. Now it starts raining. And let's assume that rain is given by, is time varying, is varying in time. And let's say that for the first area we have a rainfall intensity I1. At the end, for the first area, we have a constant rainfall intensity. This is a simplification. Not A, sorry, I1. Okay, what happens after 1 hour then? After 1 hour, during this hour, we observed a constant rainfall intensity I1. After 1 hour, we have this part of the catchment that is contributing to the river flow. And what is then the river flow after 1 hour? Q1 is equal to I1 times A1 times C. Is this clear? Okay. Now, second hour. Rainfall I2. What happens? So, rainfall is still uniform within the hour, but different with respect to the first hour. Now, what happens at the end of the second hour? We have a Q2, which is given by I2 times A1. Why this? Because rainfall that fell over this area in the first hour is already passed through the closure of the catchment, or the rainfall. Because the time taken by this area to reach the closure is 1 hour. So at the end of the first hour of rainfall, this area has already contributed, and all the rainfall that fell in the first hour passed through the closure. In the second hour, see, in the second hour, we have rainfall that occurred in the second area over A1 that is contributing. Plus, be careful, area A2 that is now contributing, because after 2 hours we have all this area that is contributing, because the travel time is 2 hours, but is contributing not with the rainfall of the second area, just with the rainfall of the first one. So we have plus I1 times A2. This is what's happening. Now let's go to the third hour, Q3. And in the third hour we have rainfall I3. Again, I3, sorry, I forgot the C here, times C times C. Let's assume for simplicity that C is not changing in time and the different hours. Of course, you could allow it to change, but for simplicity, just for not complicating things, let me assume that it's constant. Okay? So here now we have at the end of the third hour, I3 times A1 times C plus I2 times A2 times C plus I3 times A1 times A3 times C. This is what's happening. And so forth, but I said, and so forth, but with some change, of course, because if you move on one more step forward for the fourth hour, then of course you don't have A4 contributing. So you have to change this scheme here. Let me stop at the concentration time, okay? Because if we stop here, we can make this write in general, and we can write it in this way. Qn is equal to the summation from k equal 1 to n of I. Okay, let me bring C outside. It's constant. outside, I bring it outside the summation, okay? So here I have I n minus k plus 1 times A times A k. Yeah. This is the general writing. Look, this model allows us to get not just the peak flow, but a complete hydrograph. And with a time varying rainfall, which is already a complication, with different inter areas between isolines. So it's, with respect to the rational formula, it's more complicated. And from this, you can get the rational formula as a special case. Because if you are just interested in the peak flow here, and you assume that rainfall intensity is constant, not changing in the different hours, then you get the rational formula. Because with the same rainfall intensity, after 3 hours, you get from this summation that the flow is given by C times the whole area of the catchment times the uniform rainfall intensity. If you try to make this summation by what do you get if you assume that rainfall is constant, you can bring rainfall outside the summation, so you get that Q is given by C times rainfall times the summation of the inter areas, which is the total area. So you get the rational formula as a special case. But I want also to make clear that the rational formula came first, this complication came later. And it followed a logical scheme. People were no more satisfied by the rational formula only, and they tried to extend the reasoning of the rational formula to get the whole hydrograph, and they got the time area method. Okay, now let me put in evidence that I can write the formula of the time area method by using an integral instead of a summation. Because if you allow these inter areas to become smaller and smaller until you get infinitesimal values, you get an integral. And it's quite easy. Before writing the integral, I want to make clear that in my slides, the index here is just n minus k, because the slide is taken by a textbook that is available on the web, but I realized I didn't have time to change, I apologize for that, but I realized that you need a +1 here. So if you make a comparison with my slides, that I couldn't project now, but now I'm going, during the break, to take the table I will show you. I think this is my reasoning, but I think I am correct. You need a +1 here. So I think there is a mistake there. Okay? I will change it, but I didn't have time to change. It's written by hand, and it's a textbook that is available on the web by a famous professor, but I think there is a mistake. So let's write an integral here, and let's write that qt, because you remember this n here is a temporal index, because we make reference to 1, 2, 3 to the isolines, and the isolines refer to a time. So this is a temporal index. So I can write it qt, meaning that I want to identify the river flow for an arbitrary time, not just a discrete timing given by the position of the isolines. Okay? So let me try to write it as an integral between 0 and t. The summation is between k equal 1 to n because it was a summation extended from the first timing of the isoline to the last one. So I can change it with an integral between 0 and t. And in this case, let me write Tc here, which means time of concentration. And what should I put here? First of all, the runoff coefficient outside, which is constant. And then here we can write It, which multiplies, here let me put a d tau, which is the integral variable. It indicates a time, of course. The integral is varying between 0 and t. What should I write here? Instead of ak, k is a time. What is A? Is the interarea between two subsequent isolines. So it's the change in contributing area in time. If I indicate with AT the area that contributes to the river flow at time t, AK indicates the change at the given time in contributing area. Please become familiar with this term. Contributing area means that at a given time you have part of the area of the catchment, possibly the whole catchment, that contributes to the river flow. What does it mean that contributes? It means that rainfall falling over this area is contributing to forming the river flow at the outlet. Therefore, we call it contributing area. It means that at the given time, this area is contributing to the river flow. After 1 hour of rain, you have all this area here that is contributing to the river flow. Now, if AK is the change in contributing area, here I should write the AT over T. This is the change. In contributing area. In the tau, sorry. The tau, because this change in contributing area is computed at time tau. Now, this is an integral that describes my model, and interesting. And you understand now the importance of this derivative of the contributing area over time. And you could also write a graph that, depending on time, on the abscissa, depicts the contributing area along the ordinates. And it starts from 0, 0, of course, because at time 0 you don't have any area contributing, and it gets to a point whose coordinates are TC and A. The shape is whatever. whatever, but it could be linear. Could be linear. If it is linear, what does it mean? It means that okay, now let me drop this concept because it's too. If it is linear anyway, it means that, of course, the contributing area is a linear function of time. Of course. And there is an important result that I'm mentioning to you, but I don't prove it. I don't want to prove it because I guess that you already proved it during your hydrology course. And this proof takes some time. And so I don't want to prove it. I just want to remind it to you because I think it's an important result, but I'm not proving it. And I was saying it can be proved that if this curve is linear, usually this is called, in Italian is called curva area tempi, in English is called time-area relationship. And if the time-area relationship is linear, first assumption, so T are linear, two, second assumption, if I, rainfall intensity, average rainfall intensity over a duration of rainfall D, if this rainfall intensity can be written in this way, I equal a coefficient A, lowercase a, times